All right, let's get right into it. If you've ever found yourself prepping for a coding interview, you know the feeling. Analyzing recursive algorithms can get, well, messy and fast. But what if I told you there's a shortcut, a really powerful one? That's the master theorem, and we're about to make it your new best friend.
So here's the big question, right? You've got an algorithm that's calling itself, splitting a problem into smaller and smaller pieces. How in the world do you figure out its runtime without getting totally lost in the weeds of complex math? It seems impossible, but I promise, there's a much cleaner way.
The secret really lies in spotting a pattern. See, most of these divide-and-conquer algorithms, the ones that break a big problem into smaller versions of itself, they all follow the same basic structure. It's like our recursive riddle, and once you learn how to read it, you're halfway to the solution.
And this equation right here, this is the riddle. Now, I know it looks a little intimidating, but let's break it down. T of n, our total runtime, is made up of just a few parts. A is just how many smaller problems you're making at each step. B is how much smaller each of those problems is. And f of n, that's just the work you have to do to split the problem up and stitch the answers back together at the end. That's it.
Okay, here's where it gets really fun. Instead of thinking about this as a math problem, I want you to think of it as a battle. It's a tug-of-war happening inside your algorithm between two competing forces, two different kinds of work.
On one side of the rope, you have the effort it takes to combine all the results at each step. And on the other side, you've got the sheer, overwhelming number of tiny little problems you end up solving at the very bottom of the recursion. The master theorem is all about figuring out which of these two forces wins this epic battle.
And this lays it out perfectly. On the left, you have the work to combine, which is that f of n part. Think of it as the work you do at the root of each little problem. Then on the right, you have the work at the leaves. This is the total cost from all those tiny base cases, and that number can explode depending on how many subproblems you create. So who's stronger? The referee in this battle is this little value right here, c, which is log base b of a. Just think of c as the tipping point, a critical number that tells us how fast the number of subproblems is growing. All we have to do is compare the work at the root, f of n, to n raised to the power of this critical c. That comparison tells us who wins.
So you do that comparison and what happens? Well, there are only 3 possible outcomes. That's it. 3 scenarios, each declaring a clear winner and giving us the final runtime. Let's look at the ultimate cheat sheet for this.
This table is everything, seriously. Case 1, if the combination work, f of n, is lighter than the work at the leaves, n to the c, then the leaves totally dominate. The runtime is just theta of n to the c. Case 2, if they're pretty much balanced, it's a tie. The runtime is almost the same, you just multiply it by a log n factor. And case 3, if the combination work is way heavier, then the root dominates, and your runtime is simply whatever that work was, theta of f of n.
Okay, theory is cool and all, but let's make this concrete. We can actually use this cheat sheet to analyze some of the most famous algorithms out there in just a few seconds. And this isn't just about passing an interview, you know. Understanding these forces helps you actually design better, faster algorithms from scratch.
Okay, first up, the classic, merge sort. Let's break it down. Merge sort splits the problem into 2 halves, so A is 2 and B is 2. The work to merge those sorted halves is linear, so f of n is just n. Easy enough. Next, we calculate our critical exponent. C is log base 2 of 2, which is 1. Now for the final showdown. We compare f of n, which is n to the power of 1, against n to the power of c, which is also n to the power of 1. It's a perfect match. That's a tie, which puts us right in case 2. And the result? The famous theta of n log n. Boom! Let's do another one, even faster. Binary search. Here, we only make one new subproblem out of the half that's left, so A is 1 and B is 2. The work at each step is basically nothing, just a single comparison. So f of n is a constant, we'll just call it 1. Now for C, log base 2 of 1 is 0. Time to compare. Our f of n is 1, our n to the power of c is n to the power of 0, which is also 1. It's another tie. Case 2 again. So we get n to the power of 0 times log n, which simplifies down to just log n. See how easy that was? All right, let's look at a wilder one, something like a fast multiplication algorithm. This one cleverly creates 3 subproblems, each half the size, and takes linear time to combine them. So A is 3, B is 2. Our critical exponent C is log base 2 of 3, which is around 1.585. Now the comparison. Our combination work f of n equals n grows way slower than n to the power of 1.585. The leaf work is growing much faster. This is a clear win for the leaves. That's case 1, and our runtime is theta of n to the c, or n to the power of log base 2 of 3.
The master theorem feels like a superpower, right? But even Superman has his kryptonite. And knowing when you can't use the theorem is honestly just as important as knowing when you can. This is the kind of stuff that separates the pros from the novices in an interview.
So you've got to remember these edge cases. The theorem falls apart if your subproblems aren't all the same size, like in the worst case of quicksort. It also doesn't work if A or B aren't fixed constants. For case 3, there's a special catch called the regularity condition. It basically makes sure that the root is winning by a lot, not just by a little. And finally, if the battle is just too close to call, if the two sides are only separated by something small like a log factor, the basic theorem just throws its hands up and can't declare a winner.
And this quote really puts it all into perspective. The master theorem should be your first choice because it's insanely fast. But for those tricky cases where it doesn't apply, you have to reach for more powerful, but also more complex tools, like drawing out a full recursion tree or using the more advanced Akrabazi theorem.
And that kind of leaves us with one final thought, doesn't it? The master theorem gives you the answer. It's the shortcut. But sometimes the real deep understanding doesn't come from the shortcut. It comes from taking the scenic route, from mapping out the recursion and really seeing how all the pieces add up. The shortcut gets you the answer, but the long way, that gets you the insight.